here, I'll do this. After one period, didn't write that very clearly, but what does that mean in equations? It means that omega times t has to equal 2 pi. That's what it means, right? And so what does that tell us? It tells us that omega equals 2 pi over capital T. We've got a name for 1 over capital T. That's f, right? So this is 2 pi times f, and that's the relationship I'm looking for between my two types of frequencies. So this is angular frequency. Whenever you hear the word angular, most of the time it means there's a 2 pi floating around, right? And there it is, multiplying by my plain old regular old f frequency. So this is the number of cycles per second. This is the number of what per second? Degrees? Radians. That's right. So implicit in all this stuff, right, is that when we talk about angular frequency, it's really we're talking about radians. We're not talking about degrees or some other measure of measuring angles. We suppress that though when we do our unit analysis, just like we did with rotary motion. So when I'm looking at an equation like this, and there's an omega in some part of it, and there's a square root of k over m and all this stuff, and I'm checking the units work out, I don't say radians per second. I just say 1 over second, right? But in order to make all the numbers work out and have it all make sense, we have to remember that omega is going to be in radians. Yeah, don't use degrees, right? Yeah. Okay, good. So good. So here's another equation. So when you get into oscillations, and then we get into waves as well, we get lots and lots of. It turns out there's a lot of degeneracy or redundancy in a way. There are many different ways to express the same thing. Like we can write a whole problem in terms of omega. We can rewrite everything in terms of f, right? They convey the same information. There's just 2 pi between them. Same thing, and also period. Period. Capital T and omega and f are sort of interchangeable, right? We don't have to have all of them. The reason we define them all though is that some of them are more useful than others for compact notation. Like it allows us to get rid of the 2 pi's in some expressions, and also there's physical meaning to the period. If you just start thinking about what the period meant before we ever had a notion of angular or anything, we didn't even think about sine waves when I first drew that thing up there. So and there's historical reasons as well. So the result is there's lots of variables floating around, and only a few of them are linearly independent of another. There's only a few different variables you need to specify the whole problem, but there's a lot more floating around you can use to describe it if you like. So just be aware that there's a lot of redundancy for oscillations and waves in terms of the way you can express the same thing. Okay, so one thing to introduce too now is the notion of phase, and I'll do it this way. I'll say, suppose if you may be given a problem where, okay, the mass of the object, the spring constant of the spring, k and m, right? But you're also told something about the initial condition of the problem. Like, well, at time t equals 0, the mass is moving at some speed, or it's displaced by some amount, which may not necessarily equal the amplitude, right? You might be given some initial conditions that don't line up nicely with a nice picture like that, cosine or sine, right? So the way you have to handle that is by adding a phase. What do I mean? I mean that x will wind up being a times cosine, say, of omega t plus an extra piece. This is what I'm referring to as phase. So this is kind of convenient. Phi for phase, right? To help us remind us what that means. So this does not depend on time. It's just a constant that's added on. And it has the effect of just shifting the whole picture over. Now, when you take your derivatives, it winds up not playing any role because you do your chain rule, right? Take your derivative with respect to time. Okay, you get the same thing. You get a minus a times sine of the same argument, and then take a derivative of this argument with respect to time. Well, you get the same old omega factor in front like you got last time because there's an omega t here. But this doesn't depend on time. So a derivative of this with respect to time is just 0, right? And you can forget all this after I finish saying it because you're not going to ever have to take these derivatives really in any exam. You may see it on a homework problem or something like that, as you're used to now, but you don't see it on the exams. But it helps you think about where all this stuff comes from. The upshot is that if you start off with a cosine of omega t plus phi, and then you go through all your derivatives, when you're done, when you get your velocity and your acceleration, you stick them in your Newton's second law and everything else, all the arguments of all your trigonometric functions look the same. They all have the phi inside. But you don't get anything different in front as a result because it doesn't depend on time, so the chain rule doesn't get anything extra. All right? So that's good. And let's figure out which way the curve is shifted with a positive phi. Right? So if phi equals 0, we get the picture we have on top. Right? At time equals 0, you put 0 in for t. No matter what omega is equal to, this is going to wind up being 0. So if this is equal to 0 too, cosine of 0 is 1 times a is a. That's your max. So you wind up with that picture on top where you start off with the maximum and then you fall off. Now if phi is positive, the question is, what do I have to do to make this argument for the cosine, the argument of the cosine, what do I have to do to make this whole argument 0, which is what used to happen at t equals 0? Does t have to, so suppose phi is a small positive number, smaller than 2 pi. When I say small, I mean smaller than 2 pi. Maybe it's equal to 0.1 or something. Some small positive number. Now, do you want to have a small positive or small negative t to make this argument go to 0? Is it clear what I'm asking? I'm trying to figure out which way am I going to shift the cosine wave to make this argument 0. Yeah, more negative. If you have a small negative number here times another number, you get a small negative thing here. Small negative thing plus a small positive thing equals 0. Good. So if I have a positive phi, it has the effect of shifting the curve to the left. So let's draw a picture of that. Or I'll distinguish it from the previous steps. Let's say we're drawing a different situation here. So once again, I've got time along this axis. So I've got x up here, and I've got some non-zero phi. Now if phi equals 0, it would have started off right at a and gone. This is what it used to do, right? And so on. But now what I've done is I've added a positive phi. That has the effect of shifting it back to here. See that? So this is what it looks like. Everything else about the wave is the same. It used to have certain, used to have some particular period and frequency and the rest of it. Well, everything's the same, it's just that it moves it over. And it moves it to the left because that means there's some negative time value, right, that I have to stick in order to cancel out the positive phi. Exactly what is it? Well, if I let t be negative phi over omega, that's exactly how far I've shifted. Negative phi over omega. So it's good to be able to think through this stuff. Be able to figure out which way does the curve get shifted, right or left. I mean, the rule of thumb is positive phase in here, move your curve to the left, right? But I don't bother to remember it that way. I just go through and think it through each time because I'm likely to make some minus sign error somewhere else. So I just think through what would the curve look like. And that's what happens. It shifts over to the left. When we get to waves, we'll have to think about this both in x and t. And there's a lot of stuff going around. So it's good to be able to think through what happens. Anyway, great. So that's the idea of a phase. It allows you to match the conditions of the problem. After all, it's not always going to be the case that time equals 0. Like there might be some other specification about what happens at time equals 0. You may have to have the mass moving and not right at the equilibrium position. So you want to use a sine or cosine, right? If that's true, just match up your initial conditions to make things work out. Figure out what the argument has to be to achieve whatever the conditions are, and then solve for the whatever part it is you're looking for. But it's, I guess in this case, for phi. Okay, great. So you've got 3 things you need to specify a given sine wave or cosine wave. You need the amplitude, you need the phase, and you need the frequency, the angular frequency. And then you have a bunch of other variables you can use to describe it. Okay, let's talk really quick about another kind of shift, and that is vertical versus horizontal springs. This has come up before because we've had springs in the class before. But if I had this spring, say, on the table, laying down its side, or even right now, if we assume that's a massless spring, okay, so the spring doesn't have any mass, so that it's not stretching itself. If it were massive, right, it would be hanging down a little bit. And of course, it is a little bit massive, but we'll pretend it's not. It's an ideal spring. Well, that means that this equilibrium, the length of the spring right now is the same as it would be if I laid it on the table on its side, right? And if I put a mass on the end of the spring and then pushed it, and so this is sort of a funny example because this spring is, it's not so, it's a kind of spring that when it's in equilibrium, it's almost compressed all the way it can be. So instead, think about a spring that's like the springs on your car and the shocks in your car, right? if you have a big heavy-duty spring that can actually, it exerts a force when you compress it, it pushes back that way, and when you stretch it, it has a force going, well, restorative in either case. You compress it, it pushes it that way, you stretch it, it goes that way. Think of that kind of spring. So in that case, it doesn't matter when you lay it down or hold it up like this, how long it's going to be, as long as it's ideal, doesn't have any mass. When you put a mass on the end, now you stretch it out some, right? It's a new equilibrium position. There's two ways to handle that. One way is to explicitly include in all of your equations the force of gravity acting on the mass, right? So let's make a free body diagram. See, all right, I got my free body diagram for my weight, right? And let's do it for the vertical case here. See, all right, well, I got my, so I've got my spring, right? There's a mass here. So what's the free body diagram? That's not my free body diagram. That's just a picture of the situation. So the free body diagram says, okay, there's an upward force. Well, let's say we know if it's holding still, we know it's an upward force in the spring because there's only one force in the problem, that's gravity. So you've got mg going down, and I've got a force upward that's equal and opposite to that, which is the restorative force of the spring. It's the force of the spring on there, right? Well, I know from Hooke's law, I can figure out how much displacement is needed to produce that force, right? So I'd say, well, how far is it below its equilibrium position? So let's call it delta x, the displacement from the equilibrium position. And by equilibrium, I have to be really careful. This is displacement from the new equilibrium position with the mass on it and the original equilibrium position when it was on its side, or when there was no mass hanging on it. That's what I mean by delta x. I mean the difference between the equilibrium positions. Equilibrium position, so I'll abbreviate it. Position, between the two positions, the initial and the final one. And so what is that equal to? Well, we'll use Hooke's law, right? Hooke's law says force of spring equals negative k times, times delta x. So there it is, right? So in other words, there's two ways to think about it. One way is I can think of this thing now as a system where I'm just going to absorb the force of gravity. So the force of gravity is a constant. Right? It's always going to be acting the same amount on its mass, no matter what its displacement is, no matter how fast it's moving. So that means I can just sort of absorb it into the force, like have a combined force of the spring and gravity. In that case, I'd say, oh, there's an equilibrium position for that combined set of forces, gravity plus spring. Here it is. Let's call this x equals 0. Here's my x-axis. We'll call this x equals 0. That's one valid way to handle this. If you do that, though, you'll have to redefine. If you add some more mass on, there's a new equilibrium position, right? If I add a little more mass on, it goes down further. So I got to do it. So just make sure you keep straight that you've got a different one for different masses. But once you do that, everything's the same. It's as if it's like you remove gravity from the problem. If you want to calculate what's the oscillation frequency now for this system, it's the same as it would have been had you put the spring on its side and these guys were just sitting on the end of the spring oscillating. Right? Gravity, in other words, the strength of gravity acting on these things, the force of gravity on these masses, does not affect the oscillation frequency. It just affects where the equilibrium position is. And another way to handle it, so that's one way to handle it. Another way to handle it is to not redefine your equilibrium position. Just keep calling this the equilibrium position, and keep the force of gravity explicitly represented throughout the entire problem. And then this right here, this delta x, right? That's just what you get from Hooke's law, right? From that equation right there. And you just keep it around. Either way is fine, but don't mix them up. Don't do a little one and a little the other. You'll wind up leaving something out, or you'll double count one or the other. Anyway, it's all about accounting in this class, keeping stuff straight. Okay, so that's vertical versus horizontal. One thing I want to mention too before I go on to torsion here is that with oscillations now, right? So we've got, I'll keep my oscillator going. With oscillations now, we've got a new special type of motion. Like in the beginning of the class, right? We learned about we wrote down kinematic equations that just said, okay, here's the definition of velocity and acceleration. And then we said, there's special types of motion. There's constant acceleration. There's circular motion. And there's two kinds of circular motion. There's uniform and non-uniform. And then now we're talking about another special kind of motion. We have special equations for this, right? Because it comes up all the time, and it's important. A lot of physical systems act this way. Well, one thing I want to point out is that this is actually a special case, if you like, or a way. If you think about circular motion a certain way, this is really just like circular motion, in a way. It's like if you have something that's moving in a circle. So let's say I've got a ball here. Well, they wound it up really tight for me. Can I do this during the time of the lecture? I don't know. Let's see. Oh, all right. Oh, I did it. All right. Very good. So you've seen this demo before. I swing a ball, right? Very impressive demo. If you see this from the side, right? What you're seeing actually is just like what you're seeing with that spring mass on the spring. The ball is oscillating left and right. And of course, you guys are sitting up kind of high, so you're looking down. You can see that it's going in a circle. But if you pretend, if you look at it, if you're right, somebody in the second or third row are looking at it almost exactly from the side. So what you see is just an oscillation back and forth. You don't notice the depth. I mean, you know better, but you don't see it. Right? So it turns out that mathematically, it's exactly the same. It is sinusoidal motion. In other words, if I write mathematically how I describe circular motion, and in particular uniform circular motion, I'm talking about uniform circular motion, not this. Right? If I have a ball going around here in a vertical circle, it's slowing down, it goes up here, and speeding up down here. That would not be exactly the same. But if I have something going in a circle, right, and I define two orthogonal axes, so here's the x-axis and here's the y-axis, right, and so the ball's moving, it starts off right here and it goes around like that, it's going in a circle, right, some angle theta, whatever it is, right, then sure enough, the equations of motion in x and y are simple harmonic motion, right? So if I say, all right, x of t equals, there's some amplitude a, well in this case, a is equal to r, right? The biggest excursion x ever makes, that the furthest the ball gets from the origin is when it's straight out like that, and that's the radius of the circle. So, a equals r, where this is what I mean by r, right? It's just the radius of the circle. So it's a times, let's say it's cosine theta. So if you do a cos, I should be really careful here. Theta? Yeah, we could do that. Let's see. Gotta be careful. The thing is, in this part of the class, there's a lot of degeneracy in terms of what we call the same. So, we'll see this in a minute, but we've used omega in this class so far to talk about, today we used it already to talk about angular frequency. But we've used it to mean d theta dt, right, to talk about the angular velocity. Well, that's really a different physical concept. So don't get those confused. It's easy to do that, especially when we get to torsional systems that are spinning, and the restorative torque, the torque that tries to get you back to the equilibrium orientation. When that thing itself causes an oscillation, right? Now you've got two kinds of omegas, right? But anyway, just a heads up, we'll get that in a minute. So you have a times cosine of what? Well, let's say omega t, right? And we can add some phase, but let's not. Let's just go ahead and see that. So if that's our x of t, what does y look like? Well, let's see. If the ball is going that way, counterclockwise around a circle, and at time equals 0, well, stick in t equals 0, what do you get omega times 0, 0, 0. Cosine of 0 is 1, so you get a. So it starts off right here. At time equals 0, here's where the ball is, right here. What does y equal? Well, better equals 0. If this is my axis, here's my origin, right, 0, 0. So that means that at time equals 0, I better have a 0. That means it's going to be a sine wave, not a cosine wave, right? So what does that equal? It equals, again, a is the biggest excursion it ever takes. This is the radius of the circle, so you get a in front of both. You have sine here, and you get the same argument, omega t. So when this is maximal, right, when you get to pi over 2, and sine of meaning omega times t is equal to pi over 2, right? In other words, when little t equals capital T over 4, not to a quarter of a period, right? That takes you from here to there. Let's see, I better get a positive value as I've drawn it, and that's correct. This is positive because I know y starts off going in the positive direction. Anyway, all I'm doing is I'm writing down these two functions and then figuring out that it's positive here and what all these things based on the physical situation that's being described. But what you see is that when you look at something that's moving in a perfect circle in a uniform circuit of motion, you look at it from the side and calculate exactly what its position is along the dimension that you're aware of, right? It's exactly the same as simple harmonic motion. This comes up all the time, right? So that means if you have a mass on a spring, and the spring is a two-dimensional spring, it'll provide a force restoring it toward the center, and you pull it out a little ways, and you push it that way instead of that way. Instead of oscillating back and forth, it's going to go in orbit. And in fact, that's what we're doing right now around the sun, right? Although I should be careful because the force between us and the sun is not given by Hooke's law. Right? In fact, the force from the spring increases as you stretch the spring. The force from the sun to the earth, it actually goes down when you get further away. It goes like 1/r squared. We don't actually cover that in class officially, but I decided to throw it out there. But if you stay the same, but the analogy is good if you don't change the distance. If you're going in a perfect circular path, so that the distance is always the same, the force magnitude is the same. All that's changing is the direction of the force. And in that case, yeah, when you go around in a circle, you're always falling into the, you never make it. You're going in a circle. Same thing would happen with a spring. If you had a spring with a ball in the end, and you have it go around like that. Yeah, it's always pulling it. There's always a force back toward the middle, but it doesn't come back. And it's still undergoing simple harmonic motion in each of those two directions, in both x and y direction. You can also have situations where it isn't in a perfect circle. You can have other kinds of motion. But anyway, this is the one I want you to understand, though. Circular motion gives you simple harmonic motion in each of the two, any pair of orthogonal directions you choose. Any line you take in the plane, say how do you describe along that axis? It's simple harmonic motion. Okay, great. Special motion. What's next? Yes, the torsion pendulum. All right, so as advertised, we can do all this stuff for a torsional pendulum. So what does that look like? This thing, here I get the camera back over here. This thing is it has a stiff wire, like a piano wire or something, and it doesn't like to be twisted. So, and this thing down here is hanging on the wire, and there's a little line in the front, a vertical line. And if I twist it over to the side, you see there's a force that tries to twist it and push it back to where it was. So here's the equilibrium position. If I go the other way, the sort of force goes the other way. So if I go like that, it oscillates back and forth, right? So this is an example of this is a restorative torque, right? This is an oscillator that's a torsion oscillator, I guess you call it. And it also depends on stiffness of spring. So if I have a stiffer wire up here, it would have a faster oscillation, a bigger omega, right? And if I add more mass, what's going to happen if I add mass to this thing? Is it going to make it? I mean, by analogy with this, with the mass on the spring, would you expect it to be faster or slower if I add more mass? Slower. That's right. Let's see if that's true. Yeah, right? Slower. 1, 2, 3, and there it goes. Sounds like an Edgar Allan Poe. Watch me do this up here. Must be horrible for you guys. Anyway, much faster. 1, 2, 3. All right. Shocker. And the way that, and we can work out the math there. The math is exactly the same. So what you wind up with, I'll just write the initial equation down, but everything follows the same way. What's our situation? Our situation is a second order differential equation, but now we're starting from Newton's second law for acceleration, right? For angular acceleration, I mean. The rotary motion version of Newton's second law, right? And so what does that look like? It's the net torque equals I times alpha, right? Combined with a Hooke's-like law for torsion. And so what does that look like? Hooke's law would say that the torsion from the spring equals negative kappa, so just a k with a funny little doohickey on the side, right? It has different units than k, so we get a different name. Kappa times, well, let's see, what should it be? It should be displacement in angular space. So it should be the angle that you actually rotate the thing, theta. So instead of x, you get theta. Instead of k, you get kappa, right? And anyway, it's all the same, right? So what is our net force going to be? Well, in this case, torque, I should say. The only torque in the problem is this wire. So you combine these things, right? And what do you get? You get that negative kappa times theta equals I times alpha. What is alpha? It's the second derivative of theta with respect to time. Right, so it's exactly the same equation we had before with the minus sign, but now instead of having m over k, we have I over kappa. So the result is that omega. Now be really careful here. Omega. By this omega, I do not mean d theta dt. Right? That's not the same thing. So maybe I'll call it omega oscillator. This is the angular frequency of the oscillator. Right? This thing we'll call it omega. These are different omegas. Yeah, I don't know how else to say it. Yeah, it's really terrible the number of ways you get confused by all this stuff. So we have omega oscillator. What is that equal to? It's equal to the square root. And instead of being k over m, it's kappa over I. So everything's the same. All the math is the same, but we're in a different space now, right? We're in a space of this rotary motion space, theta space, not x, not a linear displacement space. That's all. Yeah, the main lesson I'm trying to give here is just be aware of the fact that there are these different things with the same name. Yeah, a lot of stuff. Okay, so now, probably one of the most important oscillators around, right? Oh, yes. Yeah, that's great. Yeah, that's a good question. Where's the torque acting? So, right, so like on Thursday's exam, there might be some torque on there, right? And you're going to have to calculate torques from individual sources. There's some force acting on some rigid object, and there's a pivot point you've chosen. This is a rotary motion problem, so you're not allowed to choose any old point for your pivot point. You can choose the center of mass, or you can choose the stationary point. Well, in this case, the stationary point is the center of mass, so your pivot point's decided, right? It's right in the middle. Like the axis of rotation is exactly the same as the axis of this wire. I mean, you might complain, well, not exactly, it's sort of bent. Okay, fine. If it weren't bent, that'd be perfect. So yeah, that's a great question. So you're saying, well, there's forces being acted right along that axis because of this thin wire, but that's not the way you calculate torque. We calculate torque, like it should be zero, right? There's forces, but the reason it's not zero is that if we look really closely at this wire, right, we would find that it does have some spatial extent, and even though the wire is really, really skinny, the fact that it's a little bit off axis, right, allows it to exert a force that way. Like when I spin the thing this way, there's a force from the wire on this piece of metal here that's, well, on that side of the wire is pushing that way to torque it like this. And it's a really big force, very close to the